Hello, this is Jack Jackson. In this video, we're going to talk about the integral test for series convergence. In this section, we'll introduce this test and explain why it works. When we can apply it, this test will not only determine if a series converges or diverges, but it also gives us bounds on the size of the limit when the series does in fact converge. The basic idea behind the integral test is to approximate the integral with a Riemann sum where delta x is 1. The infinite Riemann sum is the sum of a sequence. To see how this test works, let us start with a sequence that has only positive terms and is decreasing. For example, let a sub k be k to the negative 1/2 power, or in other words, 1 over the square root of k. Now consider extending the domain to all positive numbers, and we have the function f of x equals x to the negative 1/2, or in other words, equals 1 over the square root of x. We just changed the letter k to x, but now we're thinking of not just changing the letter, but replacing where it's k was only a natural number, x is any real number. Now what do we want? We want to have f of k equals a sub k. We get that automatically by just changing the k's to x's. But we also want f to be decreasing on the interval from 1 to 0. We need a little bit more than that. We need to be f is a positive value, decreasing, and we want it to be continuous on the interval from 1 to infinity. Now consider the integral from 1 to n plus 1 of f of x dx. Since f of x is positive, this represents an area between the curve and the x-axis. If we approximate this integral with the left Riemann sum, with delta x equals 1, then the area of each rectangle in the approximation is exactly one term in the sequence a sub k. The first rectangle has area A1, the second rectangle has area A2, and so on. Therefore, the sum of the first n terms of the sequence is this left Riemann sum. Approximation of the integral. Here's an illustration for this problem where n is 25. So here we have the curve. In this case, it's f of x is 1 over square root of x, but it can be for any curve that is decreasing, positive, and continuous. But we want, when we put in x is a whole number, a natural number actually, 1, 2, 3, that the height of this curve right there, which is the height of that rectangle, and it's also the area of that rectangle, is the same as the term. In this case, A1 for the first one, A2, and so forth. So this one is 1 over 1 square root of 1, which is 1 high. The next one is 1 over square root of 2 high. The next one's 1 over square root of 3, both height and area because the width is 1. If you add up those from, say, 1 to 25, you get all the sum of these areas here. That's an approximation of the integral from 1 to 26 of this function. Okay, so it's approximated by the sum s sub n is approximately the integral from 1 to n plus 1. But look, it's an overestimate always. So that tells us this integral is going to be less than the sum. The integral from 1 to n plus 1 of f of x dx is less than that sum s sub n, or the sum from k equals 1 to n of a sub k, because the function's increasing. Well, taking the limit of this expression here on both sides as n goes to infinity makes both of these limits, these go to infinity, and it says the infinite integral from 1 to infinity of f of x dx has to be less than or equal to the sum from k equals 1 to infinity of a sub k. So on the left we have an improper integral. On the right we have an infinite sum of an infinite series. Notice when you have a less than b, and then you take the limit of both sides, you're going to end up with the limit is less than or equal to the limit. So in other words, the strict inequality here of less than, or same for greater than, is going to switch to the or equal to for Persian. So less than is going to become a less than or equal to. So it's possible these two things could possibly have the same limit. That's one of the things that that happens with properties of limits. But otherwise, this one on the left is going to be smaller. So we have this. Now, from this, we can conclude if this limit diverges to infinity, right, then this sum is also going to diverge to infinity. It's got to be at least as big. So if we can show that the integral diverges to infinity, so does the sum. Now let's use a right Riemann sum, okay, this time. And so we're going to take our same integral from 1 to 26 in this case, right, or 1 to n here. And that integral is, the sum is less than the integral. Okay, so we're going to integrate from 1 to 26. Well, sort of the sum. We've left off one rectangle. If you look, those red rectangles are the same as these blue ones, except we got a shorter one at the end, but we're missing this first piece here. Okay, so we're going to sum up the rectangles from 1 to n plus 1. Let me see, let's start back up here. From 2 to n plus 1. So this is a sub 2 for the first one, a sub 3, a sub 4, a sub 5, a sub 6, a sub 7. The last one here going from 25 to 26 is a sub 26. So we're going from 2 to n plus 1. N is 25 here, right? And we're integrating from 1 there to there. So the sum is an underestimate this time. Now we don't actually have the full sum here, so we need to add a1 to both sides here to get the full sum on the left. But what we get is the sum here, k equals 1 to n plus 1 of a sub k, is less than a1 plus the integral from 1 to n plus 1 of f of x dx. Oh, well, one thing that's nice about this is we can now take limits as we go to infinity again, and now we have the infinite sum on the left. The less than becomes a less than or equal to. We still got a1, that didn't change. This n plus 1 becomes infinity. So now if this infinite integral here actually converges, that improper integral, if it converges to a real number, just add a1 to that, and we know that this series over here converges, and not only does it converges to a less than or equal to a1 plus that whatever that integral converges to. So basically it boils down to this: if the integral converges, the series converges. If the integral diverges, the series diverges. So putting this together, we've got that the series, the sum from k equals 1 to infinity of a sub k, is greater than the integral from 1 to infinity of f of x dx, and it's less than or equal to a1 plus the integral from 1 to infinity of f of x dx. Okay, so if one of these three diverges, they all three diverge. If one of these three converges, they all three converge. But when it does converge, it gives you some bounds, a lower and upper bound. Now I could generalize this a little bit more. So, but let me state the conclusion here first. From this, we can conclude that if the function f is decreasing and decreasing continuous and positive valued, we need the continuity part because we want to be sure we can integrate it, right? So it's decreasing, continuous, and positive valued. Then the series diverges if the integral diverges, and it converges if the series converges. Furthermore, if they converge, then we have both a lower and upper bound on the sum. So here's an example, the one that we're looking at. The integral from 1 to infinity of x to the negative 1/2. Remember, our series was k to the negative 1/2, summing that up from k equals 1 to infinity. So if we could just find the integral from 1 to infinity of that, let's see what happens. Well, of course, you remember about improper integrals. The infinity is replaced by b, and then you take the limit as b goes to infinity. Now this is a proper integral for a continuous function on that interval. And so we can find an antiderivative using the power rule. Okay, that is add 1 to the power, that becomes 1/2, multiply by the reciprocal, the power puts a 2 out front. And then evaluate from 1 to b, which is 2 to the b, 2b to the 1/2 minus 2 times 1 to the 1/2, or just 2 squared to b minus 2. Okay, and then that is use the fundamental theorem of calculus. Now we take the limit as b goes to infinity. Well, b to the 1/2 or square root of b is going to approach infinity. Subtracting 2 from that's not going to change that. It's still going to go to infinity. So this integral diverges. That's the integral here. And the sum has to be at least that big, so it's going to diverge as well. So the series, the sum from k equals 1 to infinity of k to the negative 2, or the sum from k equals 1 to infinity 1 over square root of k, same thing, equals infinity, means it diverges to infinity. Okay, let's try it. Let's have you try one now. Use the integral test to determine if the series, the sum from k equals 1 to infinity of k to the negative 2 power converges or diverges. And if it converges, then give some bounds on that sum. See if you can work it out yourself. Press pause now. Okay, before we use any test, we have to verify that the hypothesis of that test are valid. So first of all, to do this, we take this function, a sub k equals k to the negative 2, take that sequence, and make a function that agrees with it by just switching the k's to x's. So we got f of x equals x to the negative 2. Well, certainly f of k is k squared, which is a sub k, k to the negative 2, that should say. Okay. So it agrees with all those. That's kind of obvious. Now, one way we have to show it's decreasing and continuous, okay? And we can basically know this. Power functions are continuous. Let's stick it there. So we got that part. How do we show it's decreasing? Well, one way we show it decreasing is look at this derivative. So the derivative is negative 2x to the negative 3. First of all, it exists, so the function's continuous. Secondly, when you take a positive number x, certainly numbers bigger than 1, but just really even any positive number, you do the negative 3 power, you're going to get a positive number. But then times negative 2 is negative. So the derivative is negative for at least from 1 on out, actually for all positive x's. And so the function f is actually a decreasing function. Okay? And it has an antiderivative we can find, so we can apply the integral test. So even if in theory the integral test would work, you still have to integrate the thing. So you have to have a function that's going to be integrable, hopefully fairly easy. Find an antiderivative in a fairly easy way. So f of x is x to the negative 2. So we're going to integrate that from 1 to infinity. It means we want to go from integral from 1 to b of x to the negative 2 dx, and then take the limit as b goes to infinity. Power rule there gives us power goes up 1 to negative 1 divided by the new power. So we get negative x to the negative 1. Evaluate from 1 to b. That's the opposite of b to the negative 1 minus a negative 1 to the negative 1. 1 to the negative 1 is 1. Two negatives make a positive, which is 1. So it's negative b to the negative 1 plus 1. In fact, let me go ahead and just write that step in. And then we take the limit as b goes to infinity. This b to the negative 1 is going to go to 0. And so the answer is just 1. So the integral does exist, and all the other hypotheses of the integral test are satisfied. So our conclusion is that the function, the sequence actually converges. Where were we? Right here. Furthermore, we can go a little further. In general, we know that the sum from k equals 1 to infinity of a sub k is sandwiched between a lower bound of the integral of 1 to infinity of f of x and an upper bound of the same integral plus the first term. First term was 1. 1 to the negative 2 power is 1. So 1 plus 1 is 2 on the top, 1 on the bottom. So we know that the series converges. We don't have any idea what it converges to at this point, but we do know it converges somewhere between 1 and 2. So once again, to use the integral test, we need the following. We need a function f such that f of k is a sub k for some natural numbers k. We need f to be positive valued, decreasing, and continuous on the interval 1 to infinity. And we need to be able to find an antiderivative for f so that we can use the fundamental theorem. So if you use the integral test, then you have to verify these conditions in the first two bullets, and you will have to use the antiderivative, the fundamental theorem of calculus, and a limit to see if the integral converges or not. However, we can relax these restrictions slightly. Certainly, the sum of any finite series converges to some number. So if we can just get the conditions above to be true for x and k greater than some natural number m, then we don't have to worry about the first m terms. In general, when we perform convergence tests for infinite series, we only need the hypothesis of the test to be true from some natural number on. The first finite number of terms always sums to some constant. The question is if the infinitely many terms of the tail converges to a constant or not. So if there are some, say, negative terms at the start, or if the function is not decreasing at first, that's not a problem, as long as the terms are all positive and the function decreases for some point forward. And therefore, we can have a slightly more general version of the integral test. And here's the more general version. So this is the integral test. If f is positive value, decreasing and continuous function on the interval from m to infinity, with f of k equals ak for all natural numbers k, say, greater than or equal to m, then the sum from k equals 1 to infinity, that should say, converges if and only if the integral from m to infinity converges. Of the integral from m to infinity of f of x dx converges. Furthermore, if the series converges, then we have the following bounds on the sum of the series. The series is here in the middle, sum from k equals 1 to infinity of a sub k. It has to be bigger than, well, the sum of the first m terms, k equals 1 to m, and then integrate from m plus 1 to infinity f of x dx. And then it's less than the sum from k equals 1 to m of a sub k plus the integral from m to infinity of f of x dx. If we replace these guys here with the s notation for sums, the sum of the first m things can be written as sm, and the sum of all infinitely many is just s, or s infinity. So sm is plus the integral from m plus 1 to infinity of f of x dx is less than s infinity, or just s, which is less than or equal to s sub m plus the integral from m to infinity. So again, we don't have to worry about those first m things. We can add those up, whatever they are. And in fact, if it does converge, then the bigger you make m, the smaller these two integrals are going to be. And so what happens is, by taking m bigger and bigger and bigger, we get better and better estimates. We get tighter and tighter bounds on this here. And so we get actually pretty tight bounds if we're willing to sum a large number of finite terms, which we can do pretty easily if we have technology. So let's go back to our last example that we know that converged. We want to use the integral test and the sum from k equals 1 to 100 of k to the negative 2 to determine bounds from k for the sum from k equals 1 to infinity of k to the negative 2. So see if you can figure that out using what we just have right up here. Press pause and come back when you're ready. Press pause now. Well, if we're going to integrate from a to infinity x to the negative 2 dx, where a is a constant, doesn't matter, a positive constant, and really it can just be 1 or bigger, then it's the limit as b goes to infinity of the integral from a to b of x to the negative 2 dx. So we want a to be positive, we want b to be bigger than a. So using the fundamental theorem, we find an antiderivative. Pretty easy. Add 1 to the power, that's negative 1, divided by the new power. So the antiderivative is the opposite of x to the negative 1. Evaluate from a to b, that's the opposite of b to the negative 1 minus a negative a to the 1, that's plus a to the negative 1. And you take the limit of this first part goes to 0. Those two negatives make a plus. So we end up with just a to the negative 1, or in other words, 1 over a for the limit. So the integral from 101 to infinity of x to the negative 2 dx is 1 over 101. And the integral from 100 to infinity of x to the negative 2 dx is 1 over 100. Okay? So we can use a graphing calculator to approximate the sum of the first 100 terms. Here it is on a TI-84. Press list, which is list is right up here, so it's second and stat, and you'll get this screen here. If you right arrow to ops, you'll get the screen that I have right here. Okay, choose number 5, sequence. You can use whatever you want for your variable. I have mine in sequence mode, so when I hit the xt theta n button, it just gives me n for the variable. But you can use a different letter if you want. Use the n on the keyboard, the alpha n or alpha k if you'd rather, just any letter. So n to the power negative 2, variable's n. I'm going to start at 1 and go to 100, step it up by 1, paste it on there, and that gives us this sequence command right here, and hit enter, and it gives us a sequence. Then I select a list, which is second stat. This time I go to math, and I choose number 5 for sum, and I just want to do the sum of my answer. So it takes this list and adds all the terms together. So it's a finite sequence and adds them up. There are 100 things in that sequence, so there's a lot of arithmetic going on here, but calculator does that just great. And so that gives us a decimal approximation for there. I'm going to store that answer as something p, maybe p for partial sum, okay? Or pick any letter you want, doesn't matter. So I store that as p, and I do p plus the integral, which is 1 over 100. And we get that, and then p plus 1 over 100 there for the other integral. So this one was the integral for 101. This is 1 over 101 is this one, and 1 over 100 is the one on the right. So, and both of them are adding this partial sum to them. So the first one should be too small, and the second one should be too big. So the real sum is between these two. And so notice they agree to several decimal places. So 1.644 and 88 is too small, and 1.64498 is too big. Actually, what we really want to do is, if we're going to do this, we want to round this one, the one on the left, down, the one on the right up. So I might round that up to a 9, say, instead of an 8. Round that one down to a 4. This one down to an 8. If you have a TI Inspire CAS and ask it to sum from k equals 1 to 100 of k negative 2, it'll actually compute the exact answer as some huge fraction, which for our purposes is not really as useful as the approximation. Or you can tell it do the approximately equal to, and it'll give you this answer here. Then I can take that sum plus 1 over 101, and then the same sum plus 1 over 100. And so those two numbers are our upper and lower bounds. This one's a lower, this one's upper bound. So rounding down the lower bound and rounding up the upper bound, both to say 5 decimal places, we obtain the following bounds on the sum of the sequence of the series. The sum of k to the negative 2 is between, that should say infinity there, the sum of infinitely many terms, which I'm just going to call S, or S of infinity, I just call it S here, is between S of 100 plus 1 over 101, and on the lower end. On the upper end, it's less than s sub 100 plus 1 over 100. And then rounding this right side up and the left side down, we get these two numbers. So we see the true sum is somewhere between 1.64488 and 1.644,984. So that's hey, it's pretty close. We've narrowed it down fairly well. Let me make those the same number of digits. Let's go 6 decimal places. Okay, that's a pretty good estimate for convergent, most convergent infinite series. When we use other tests, we will not be able to determine the exact value of the sum, which we didn't here either. And and but with the integral test, we were able to get at least some good bounds. However, on this one, there's some more advanced techniques that I'm not going to go over here that some mathematicians were able to determine the exact value of the sum of this particular infinite series. And the TI Inspire cast basically, I guess, knew that and could find out and the exact value and approximate it. Turns out when you sum from k equals 1 to infinity of k to the negative 2, the exact value of that is pi squared over 6. Again, I'm not going to go over how they got that, but let's trust that that's correct. And then if we approximate pi squared over 6 to the limits of this calculator, which I think has like 12 significant digits, you get 1.64493406685, which is accurate as far as the calculator will go. And of course, that's obviously it's going to be between these two bounds that we set out. So when you apply the integral test, don't forget we changed the x's to the k's to x's, and we must also show the resulting function of f of x is positive, continuous, and decreasing, at least from some point to the right forever. Usually showing it's decreasing involves taking a derivative and setting it equal to 0. One way to show that it's decreasing is to show the derivative is always negative on that interval from some point to the right forever. Only then we take the inner. Of course, the integrand function also has to be something for which we can find an antiderivative. Hopefully, it's something that's maybe easily integrable, something that's easy to find an antiderivative for. So here's another example for you to try. Use the integral test to determine if the following series converge or diverge. If they converge, use the integral test and the sum of the first 200 terms to determine bounds on the sum. So here's two different ones. The sum k equals 1 to infinity of k over k squared plus 1. And the second was the sum of k equals 1 to infinity of k cubed over e to the negative k to the fourth. You might notice that the limit of the underlying sequence is 0 in both cases, so the divergence test will not tell us that these diverge. The divergence test is inconclusive, so we need to move on, let's say, to the integral test. See if you can work this out yourself now. Press pause and come back when you're ready. Press pause now. Well, I hope you tried these. Let's see what we've got here. So if we let, for A, we had the sum from k equals 1 to infinity of k over k squared plus 1. We let f of x equals x over x squared plus 1. Clearly, f of k is a sub k for natural numbers k. Rational functions are continuous where they're defined. The denominator of this one is never 0. K squared plus 1 is at least 1. So this function is continuous actually for all reals. All we really needed was for it to be continuous for some point to the right. And the denominator is always positive, so the function is positive when x is positive. So it's positive, for at least for positive x's, it's positive value, continuous, and agrees with the original sequence. Now it needs to be decreasing as well. To do that, to show that, we'll do a derivative. So the derivative, we're going to end up using the quotient rule. So at least for all x's greater than 1, we want the derivative to be negative. see that, we do take our function here. It's the bottom times derivative of the top minus the top times derivative of the bottom over the bottom squared. Okay, so the derivative of x is 1. The derivative of x squared plus 1 is 2x. That derivative has been computed. X times 2x is 2x squared. Of course, this just distributes here, carrying the parentheses. X squared minus 2x squared is minus 1x squared. Plus 1, I can factor a negative 1 out front, and that leaves me x squared minus 1. X squared minus 1 factors as x plus 1 times x minus 1. So we have the opposite of x plus 1 times x minus 1 over x squared plus 1. Now, if x is bigger than 1, everything here is positive. Okay? Of course, if x equals 1, this is actually 0. Okay, but if x is bigger than 1, it's negative, and so we have the function decreasing to the right of 1. So now we've established all the hypotheses, so now we have to integrate. So I'm going to just integrate from a to infinity x over x squared plus 1 dx. This is a basic u substitution. U equals x squared plus 1. Du is 2x dx. I've got the x. I'll just put it here with the 2 to make my du. This is 1 over u du. Put the 2 in. I have to balance with the 1/2 out front of the, well, 1/2 in here. I can bring it out front of the integral sign because of the constant multiple rule, and because we have a constant multiple rule in limits too, so I can bring it all the way out front of the limit. So this is the integral from a to b, where x equals a to x equals b of 1 over u du, and then take the limit as b goes to infinity. So the antiderivative there is a logarithm of the absolute value of u. Well, we evaluate from a to b, that's log of b minus log of a. I can drop the absolute values because a and b are positive numbers here. Now, when we take the limit as b goes to infinity, the log of b does it kind of slowly eventually, but eventually it does approach infinity. So that's infinitely big minus, well, log of a is some constant. Infinity minus constant is still infinity. Half of that is still infinity. And so we see that this integral diverges to infinity. So we would say our conclusion is the sum from k equals 1 to infinity of k over k squared plus 1 diverges by the integral test. So your conclusion should end up saying, you know, what the sequence is. It should say converges, diverges, and also should say by what test. And if you're going to use that test, then you've got to somewhere up here show where you've set up all of the hypotheses and prove that. You're going to have to show where you actually apply the test there. All right, let's look at one more example. The sum from k equals 1 to infinity of k cubed e to the negative k to the fourth. Let f of x be x cubed times e to the negative x to the fourth. Clearly f of k equals a sub k for natural numbers k. Because polynomials are continuous, exponential functions are continuous, and compositions of and products of continuous functions are continuous, f is continuous on all real numbers. The exponential part is always positive. E to any power is a positive. And so we just have to look at the x cubed to see what the sign is. And so if k cubed or x cubed is positive, I guess I'm talking about x's here, and x cubed is positive when x is positive, and so f is positive when x is positive. So it's positive valued. Now what about the derivative? Well, it's a product, so we're going to use the product rule. It's the first, oh, where did I go? Here we are. So it's the first times the derivative of the second plus the second times the derivative of the first. First factor was x cubed. That goes here and here. Second factor is e to the negative x to the fourth here and here. Well, this is e to the u, so the derivative is e to the u times the derivative of the u. Derivative of the u is minus 4x cubed plus derivative of x cubed is 2x squared. No, it's 3x squared. 3x squared, okay? Factor out here. Both terms have an x squared. Both terms have an e to the negative 4x, and I'm going to factor out a negative as well. So what's left here? Well, let's see, that's gone. X squared's gone, so we got one more x there and three more x's there, makes x to the fourth, and then we got a 4. The negative's out here. This is all positive, so when I factor a negative out, we get a negative here. The x squared and this part's at the front, so we just have a 3 there. And notice that that's less than 0. For x's, when x is 1 at least, 4 times 1 to the fourth is at least 4 or bigger. Subtracting 3, it's at least 1, so it's positive. X squared is positive no matter what, unless you put in x to 0, but we're talking about x is bigger than 1. And e to any power is positive. But so you got positive, 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 but then you got the negative out front. So the whole thing is negative, which means f is decreasing, at least from 1 on out. Now the integral, it turns out, converges, so guess what? The series converges as well. Okay, so we want to integrate from a to infinity x cubed e to the negative x to the fourth dx. U is negative x to the fourth, du is negative 4x cubed. We got the x cubed, put it here. With the dx, put a 4 there, put a negative 4 there, put a negative 1/4 here, which you can bring out here, and then follow the way out front. And then we're left to e to the u du. Integrating from x equals a to x equals b is e to the u evaluated from x equals a to b. Substituting back in the u is negative x to the fourth. We have e to the negative x to the fourth evaluated from a to b. Then we got to take a limit multiplied by negative 1/4. So that's e to the minus b to the fourth minus e to the minus a to the fourth. Now we take the limit as b goes to infinity. This thing, b goes to infinity, b to the fourth goes to infinity. Opposite that goes to negative infinity. E going to negative infinity makes the whole term go to 0. So that's 0. So that negative and that negative go together to make a positive. We got the 1/4 times e to the minus a to the fourth power. So so we have that. So if we start at 1 for a, okay, it's just 1/4 e to the negative 1, or 1 over 4e. But the point is it does converge to something. So therefore, the sum of the series must converge as well. Now we can go a little further and get bounds. The reason I put the a in there instead of just say 1 or whatever, I only want to do this antiderivative in this thing once. So s sub 2, so we do 200 to infinity will be 1/4 e to the negative 200 to the fourth. So if we put that in the calculator, we see that even the CAS calculator like this evaluates that to be 0. So that's 0 to so many places, probably definitely over 100 places that's 0. So for any practical purposes, that's 0. Same thing with the 200 in there. So these two integrals are so close to 0 that we can't tell. Okay, and so in any event, we get they're less than 10 to the negative 12th anyway, and if it's less than that, that's not going to affect us on our graphing calculator number of digits that we're going to show. Okay, our I think it does show 12 digits. So let me say, actually, let me go one more digit and say that this is definitely less than 10 to the negative 13th. So even rounding off, there's no way that is going to affect any of the digits here on the sum, if even if it wasn't out as far close to zero as this. Okay, but in any event, this tells us this sum that the calculator produced here is going to be accurate to every single digit that's shown here. If we could do it more accurately, we could probably do this sum more accurately. We could work this out to, probably over 100 digits of accuracy with this, because these integrals are so small. So this sum from k equals 1 to infinity of k cubed e to the minus k to the fourth converges by the integral series test, and it has this approximation 0.36788034143, and that is accurate to all of the digits shown. So in our next video, we're going to see how we can apply the integral test to work with p-series. See you there next time.